Hello everyone, in today's video we're going to be studying the Newton's second law. And this video is going to be the first video for the series of videos I'm going to be shooting for topic 2.2, forces. And studying Newton's laws is a good starting point when you're studying forces in general. And even though the actual IB past paper questions do not ask questions directly on the laws themselves, but studying these laws is very important because these laws will allow you to have the correct insight into the nature of forces in general. Okay, so let's get right to it. All right, so let's take a look at the definition of this law first. Now, even before taking any proper physics courses, you've probably heard of a couple really popular physics formula. And one of them may be something like E equal to mc squared, which is the really popular Einstein's law of mass energy equivalence. Or another law may be something like this: F equal to ma. Probably many of you have heard of that equation, and that equation is basically the definition of the Newton's second law. But that is an abbreviated version of the law, so let me write down the proper version of it. And what it looks like is the following: a sigma sign of forces, which is equal to, in other words, the net force, which is equal to mass times acceleration. So the equation itself is pretty simple. The sigma sign represents the summation of forces, meaning you're going to be taking a look at all of the forces acting on an object, and you're looking for the net effect of it, which will result in mass times acceleration of the object. And whenever I teach this law, I try to emphasize the fact that this side of the equation represents the cause, and over here, acceleration is the effect. Now, what I mean by that is whenever an object is experiencing some sort of acceleration, the cause of that acceleration is going to be always the forces acting on them. Okay? So, since you have the sigma sign, the causes may be multiple forces. Okay? There may be multiple forces acting on an object, but all those different causes combined together will have a certain net effect on that object with mass m, and as a result, the object will experience an acceleration equal to that magnitude. Okay? So taking a simple example could look like this. Let's say that there's a baseball whose mass is equal to 2 kilograms. And you exert force on this baseball and throw it to the right with 10 newtons of force. And the unit for force is going to be Newton, which is of course equivalent to kilograms times meters per second squared. Okay? So when you throw a 2 kilogram baseball with 10 newtons of force, what is it going to be the resulting acceleration of it? As the equation simply suggests, 10 newtons is equal to 2 kilograms times whatever the acceleration is, and of course that A will come out to be 5 meters per second squared. So that means as soon as it leaves your hand, it must have gained 5 meters per second of speed every second. All right? So that is the simple definition of this law, and we're going to be taking a look at different perspectives of this law in the next slides. All right, in this slide, we're going to take a look at the definition of mass. In physics, there are so many different ways we can define mass, but one of the definitions of mass that we can explore from the equation or the definition of Newton's second law is called inertial mass. Now, in order to take a look at the definition of inertial mass, we're going to redefine the equation like this. If our previous definition of Newton's second law looked like this, we're going to rearrange this equation and say acceleration is equal to summation of forces divided by the mass of the object. Okay? So we're going to leave that right there and then come back to it later. Okay? So In your previous science courses, you've probably tried to distinguish the meaning of mass and weight. You've probably already learned that mass and weight are two different things. So let's take a look at it. What's the real difference between mass and weight? One of the easy ways to draw a distinction between the two is that weight is something that depends on where you are, meaning whether you're on planet Earth or on the moon. But mass is something more fundamental, so it does not change depending on your location. So let's take a look at what weight is first. Weight is really the magnitude of gravitational force acting on an object. So weight does have something to do with mass, because an object with a greater mass will be experiencing a greater gravitational force. But weight does not simply depend on mass, but it'll also depend on the nature of the planet itself. So the gravitational pull of the planet will also be a factor. So weight depends on two things, which is the mass of the object itself and also the gravitational pull of that planet. So we can clearly see that weight and mass are two different things. But what is really the definition of mass then? Is it the quantity of an object, or how should we interpret the nature of this term, mass? If you come back over here, we can explore from this equation that acceleration becomes smaller when mass increases under the same amount of net force acting on the object. We're going to try to use that relationship in order to define mass in terms of inertial mass. And the definition of inertial mass goes as the following. Mass is the measurement of inertia. This is the definition of inertial mass. Mass is the measurement of inertia. Guys, what is inertia? Inertia is the tendency to remain its current state of motion. You've probably learned this term inertia with an example of you riding on a bus, and when you're traveling forward with the bus, if the bus suddenly stops, you feel like you're being thrown forward, right? But is it really that you're being thrown forward? Is that some kind of force behind you that is pushing you forward as soon as the bus stops? That's probably not it, and you already know that. So when the term inertia represents the tendency of an object to continue or to maintain its current state of motion, that is basically the nature of every object. That is the natural behavior of every object. Meaning, when you're riding on a bus and moving forward, and the bus suddenly stops, the bus stops because the friction between the wheels of the bus and the floor is stopping the bus. It's decelerating the bus. But you're not experiencing that friction right now. Hence, your natural response is to maintain your current state of motion or your previously moving forward motion. Okay? So that is what inertia is. And the definition of inertial mass is saying that mass is the very measurement of that inertia, the very measurement of that tendency to remain in your current state of motion. Then, remaining in your current state of motion means your velocity is not going to change. And the tendency, the greater tendency to maintain its current state of motion can be interpreted as the resistance to acceleration, because it does not want to change its current state of motion, meaning your velocity. Hence, if an object has a large mass, we can think of it as the object having a greater tendency to remain its current state of motion, meaning a greater resistance to acceleration. Meaning, even though a large amount of force may act on it, if its mass is also very large, what is your acceleration going to be? Something relatively small. All right? So in this slide, I want you to understand the nature of this term mass. What is it? It's the tendency, it is the measurement of the tendency of an object to continue in its current state of motion, meaning resistance to acceleration. All right, so another aspect of Newton's second law that you must understand is net force and how to calculate that net force. When we write down the equation for Newton's second law again, it looks like this. And this part was the net force part. And the way we understand net force is the following. Net force is the vector sum of all forces acting on an object that results in a single resultant force vector. And this is the definition of the net force acting on an object. So let's take a close look at this term, vector sum. Now, what does the term vector sum really mean? It's simple. Addition with directions considered. With direction considered. Okay, that's what vector sum really means. So in order to understand this concept properly, we're going to take a look at a simple example. Let's say that there is a really popular student at your school, and everybody wants to hang out with this kid. So let's say that I draw this popular student right here, and a group of students is pulling on this popular kid to the left, hoping that this kid will follow them and hang out with them with, let's say, 5 newtons of force. Now, another group of friends is also pulling on this popular kid to the right with 10 newtons of force. Now, what do you think is going to happen to this popular kid? Probably he'll end up being pulled to the right with how many newtons of force? 5 newtons of force. You've just done it. You've just calculated the net force acting on an object. How did you just do that? You probably said 10 newtons and 5 newtons acting against each other, so it's 10 minus 5, which is 5. And then 10 is greater than 5, so it'll end up moving to the right. Okay? That is all correct, but I want you to shift your perspective and think of it the following way. Instead of saying 10 minus 5, why don't we consider the direction and mathematically represent the direction with sign convention. So we can say to the right takes the positive sign, and to the left takes the negative sign. Hence, a rightward force added with a leftward force results in a rightward 5 newtons of force. So the very fact that the resultant force comes out to be a positive value, it means that the resulting motion is going to be rightward, or the resulting acceleration is going to be rightward. So this is the vector sum of forces, which is the way you calculate the net force acting on an object. But this case is a very simple case because the forces are aligned along a straight line, so you can assign positive and negative, just add them, right? But more complicated cases will involve forces directed at all different angles, not along a straight line. So we must be able to add those force vectors as well. All right, so this is a one-dimensional case, and in the next slide, we're going to take a look at a little more complicated case of forces on a two-dimensional space. So now we have a system of forces acting on a two-dimensional space. So let's take a look at the question first and think about how to approach solving this question. Example, the diagram below represents a box of mass m equal to 10 kilograms. And when the box experiences a set of forces as shown in the diagram, find the magnitude of the net force on the box and the resulting acceleration of the box. So we have a box sitting on a two-dimensional space, and we have three forces acting separately on this box. And we know that even though there are three different causes, the effect of these three forces will result in one acceleration, one net force. So we must find that. Now, before we delve into numerical calculations, let's kind of estimate, let's kind of try to see the resulting acceleration of the box. Now, the 300 Newton is directed to the right and upward, and 120 Newton force is directed to the right and downward. And the 150 Newton force is directed to the left. Let's try to see what's going to happen to the box. Well, it seems like two of the forces are pulling to the right, and it seems like that effect is going to be greater than the effect of the leftward force, because 300 and 120, those effects combined together will probably be something greater than 150. Now, upward and downward, well, this guy does not have any upward or downward effect, so we have to take a look at this guy and that guy. And it seems like 300 Newton has a longer vertical effect, so upward is probably greater. So this box will end up moving or accelerating in somewhat rightward and upward direction. So we can kind of estimate what's going to happen to the box. But now, let's actually do the numerical calculation to see what's going to happen to it. Now, how do we do that? We make a use of the vector decomposition we learned in topic 1. Because, like in the previous example, when the forces are aligned along a straight line, we can simply add and subtract them by assigning positive and negative signs to them, right? The problem we have right now is that these forces are not aligned along the straight line. How do we make them get aligned along a straight line? Vector decomposition. We try to see what component, out of the 300 newtons of force, how much horizontal component does it have and how much vertical component does it have? So if we can decompose everything into horizontal and vertical directions, we can simply add and subtract them, all right? So in order to do that, we're going to decompose the 300 Newton first, which can look like this, okay? And this is the horizontal component and vertical component. And since my 30-degree angle is over here, what's opposite to it is going to take the sine function. So that's going to be 300 sine 30 degrees. And if you're having a hard time understanding vector decomposition over here, you should go back to topic 1 video on vectors and take a look at that first, all right? Now, decomposing 120 Newton force is going to look something like this and that. Oh, by the way, let me take a look at this horizontal one first. Since it's adjacent to 30-degree angle, it's going to look like 300 cosine of 30 degrees. And over here, the horizontal component, it's adjacent to the 50-degree angle, and its magnitude is 120. So this is going to be 120 cosine of 50. Okay? And this vertical component is going to be 120 sine of 50. Now this 150 Newton force is not going to have any component because itself is already only a horizontal force. So in order to do a numerical calculation, we should take a look at the horizontal and vertical components separately. Horizontal, one over here, another one over here, and another one over here. And the vertical ones, one over here, and another one over here. So I color-coded differently, blue and white. So let's add and subtract them separately. Finding the sum of the forces in the y direction first, it's going to look like this guy taking the positive sign because it's an upward force, and this guy taking the negative sign because it's a downward force. So it's going to look like 300 sine 30 plus minus of 120 sine 50. Okay, that's it for the y direction. Now, calculating the net force in the x direction is going to involve three different forces. One, taking the positive sign because it's directed to the right, and another taking the positive sign because it's also directed to the right, and one taking the negative sign because it's directed to the left. Now, let's find the sum of these forces. Now, it's going to look like 300 cosine 30 plus 120 cosine 50 and then plus negative 150. So these are the expressions for the net force in the y direction and the net force in the x direction. Now all you have to do is plug these numbers into the calculator. And I'm going to say that the resulting net force in the x direction and y direction are calculated. Now, plugging these numbers into the calculator, the x direction, it results in 186 newtons of force. And in y direction, it results in 58 newtons of force. Now, what does this suggest? It suggests that, as we suspected, since both forces are positive, the resulting force must be somewhere directed to the right, like this, and that must be the 186, and somewhere upward, like this, which represents the 58 newtons of force. So the net force is probably somewhere along this line. So I can say that's my F net. Now, I've found my Fx and Fy, so how do I find my F net? Using the hypotenuse calculation. I know the base and height, so I can know the hypotenuse. How do I calculate that? It's simple. F net is equal to square root of 186 squared plus 58 squared. Okay? And when you calculate this, you're going to get F net equal to 195.7 newtons. So I know that my net force magnitude is going to be 195.7 newtons. So I know how strong my net force is. Now I need to calculate the angle at which this force is acting. And the way you do that is using the arctangent function or the inverse tangent function, because you know the opposite and adjacent. So using arctangent, y over x will give you the theta. So y was 58 and x was 186. And what it results in is 19.6 degrees. Plugging it into the calculator, it'll yield 19.6 degrees, which means your force will be directed at 19.6 degrees and with a magnitude of 195 newtons. So I've answered these two parts. Magnitude of the net force and the direction. Well, the direction is omitted, but interpreting force as a vector, I've found the magnitude and direction. Now let's answer the last part of the question. It says, and the resulting acceleration of the box. So there are three different causes, but there is only one resulting net force. Now how do you find the acceleration? It's pretty simple. F equal to ma. So summation of forces equal to mass times acceleration. Hence, 195.7 is equal to 10 kilograms times acceleration. Hence, my acceleration comes out to be 19.6 meters per second squared. All right? So it's a pretty simple calculation. I can find the net force, direction, and acceleration through the vector decomposition. So finding the net force itself is pretty simple, but the questions you will be facing from now on will maybe have one of the forces omitted, or acceleration is given and maybe some other forces omitted. So depending on the information provided by the questions, you'll have to make use of them to find the variable you're looking for. But the fundamentals are always the same. So in today's lecture, the following things are what you should remember. Number one, the very definition of net force, or the very definition of Newton's second law, is that the net force acting on an object is the cause of the effect, which is the resulting acceleration on the object. And when that resulting acceleration is calculated, we can see that it is inversely proportional to mass, because the very definition of mass, inertial mass, is that mass is the tendency, or the measurement of the tendency of an object to continue in its current state of motion. And lastly, when you find the net force acting on an object, if it's along a straight line, you can simply add and subtract them. But if it's on a two-dimensional space, you must go through vector decomposition of each force and align them in horizontal and vertical directions, and then add and subtract them to find the components of the net force. And using the hypotenuse calculation, you can find the net force magnitude, and using the arctangent function to find the angle at which the force is acted upon. And then finally, equating the net force into mass times acceleration, you can find the resulting acceleration on the object. All right, that's it for today's lecture, and in the next lecture we're going to be studying the Newton's first law.